Assalamu alaikum.
Walaikum assalam.
Any doubt from last class?
No, sir.
Okay, last class we had started about conduction or heat transfer by conduction method. So related to this part, let me give you some question. Suppose there is a rectangular block this end is connected to furnace having temperature 100 degrees Celsius. This end is connected to ice at 0 degrees Celsius. Length of this particular is 50 centimeter, 10 centimeter, and 10 centimeter. The dimension of these terms. So from this part, we have to calculate first temperature difference, second temperature gradient, third thermal resistance, fourth heat current, fifth heat reached at ice end in 1 minute, and due to which amount of ice melted. Try to solve these terms related to this expression. Hiba, Any doubt related to these terms? How to calculate?
No, sir.
Okay. Hamza, just tell me, what do you mean by temperature gradient?
So the quantity which describes like at what rate the temperature changes
With respect to
direction.
direction? Length.
Yes.
So it will be delta T divided by length. Just solve each part and send your answer, all of you. Hamza, just tell me first answer.
Sir, 100.
Good. Second one.
Sir, 2.
Since this particular length is in centimeters, so you have to first convert into meter. So 100 divided by 50 centimeter divide by 100. So it will become 200 degrees Celsius per meter. Hiba, just tell me the formula of thermal resistance. Khalid, tell me the formula of thermal resistance.
1 by K into L by A.
Good. So we must have K equals to 0.8 watt per meter per Kelvin. So 1 by K times L divided by A. In this part, L will be parallel to flow of current and A will be perpendicular to flow of current. So length will be 0.5 and area of cross section will be this term that is perpendicular to the flow of current. So length into breadth, or 1 into 10 to the power minus 2 meters square. Just put these values and simplify it. Next is heat current. According to Ohm's law, equals to temperature difference divided by thermal resistance. So first calculate thermal resistance from this part, put it in this condition, you will get amount of heat current. And then heat current equals to rate of flow of heat, or simply heat per unit time. So how much heat will reach to the ice end in 1 minute will equals to heat current into time taken. And then how much ice would melt for this particular heat. So Q is equals to M times LF. So M equals to Q divided by LF. Just simplify all these terms. Let me solve third part. 1 by K, which is 0.8, length is 0.5, area of cross section is 1 into 10 to the power minus 2. So this decimal and this decimal will cancel out. So 5, this 10 to the power 2 minus 2 on moving to numerator, it will become 10 to the power plus 2. So 100 divided by 8. 25 into 4 and 2 into this. So 25 into 5, 125 divide by 2. So it will be about 62.5. Thermal resistance. So it will be Kelvin per watt. Hamza, you got the same or something else?
I was almost near this.
Next, how to calculate heat current. So we have temperature difference 100 and thermal resistance 62.5. Or you may write 100 divided by 5 into 25 multiplied by 8. So 5 in 4 times becomes 100. So 8 into 4, 32 divided by 5, it will be 6.4 watt or joule per second. Khalid, is it clear? Hiba, any doubt?
No, sir.
Now, fifth part, we have heat current as 6.4 and amount of heat reached at other end in 1 minute. So time taken is 1 minute, that is 60 seconds. Just multiply it. 6 into 4, 24, and 6 into 6, 36 plus 2, 38. So it will be 384 joule. Now put this in this expression. We have heat. Latent rate of fusion is 80 calorie per gram. So in terms of joule, it will be 4.2 per gram. In terms of kg, it will be 10 to the power 3. It will be in denominator. So on simplifying, 384 divided by 4.2 divided by 1000. So it will be about 1.14 gram. Hamza, any doubt?
No, sir, no doubt.
Okay, just write it down. Eba, written?
Yes, sir, done.
Okay. Now, next question would be calculation of temperature of junction. Suppose you have any rod whose one end is at 100 degrees Celsius, another rod whose end is connected at 0 degrees Celsius. Let's say thermal conductivity of this is 0.5 and thermal conductivity of this is 0.3. Area of cross section from this point to this point is 2A, and area of cross section from this point to this point is A. So find temperature of junction. So how to calculate? Let me give you some hint. You'll say heat current will flow from higher temperature to lower temperature. So for this particular rod, it will be along this direction. And second rod, it will be along this direction. Since this combination is series or parallel, Hamza,
Yes, sir.
what you can say about the combination of rod, series or parallel?
The series.
Good. Simply, if there is no division of current or no division of path, that will be termed as series combination. And we know in series combination, current will be same. So put the formula of these two terms and simplify it to find temperature of junction. So HA will be Ka by length times temperature difference 100 minus T naught equals to Ka by length times temperature difference T naught minus 0. Let's say length of this particular rod is 0.5 meter and length of this particular rod is 0.4 meter. Just put the values and simplify it for T naught. Khalid, any doubt?
Sir, we have to find T naught, right?
Yes. Hamza, any problem while solving?
No, sir.
Okay. Given we have zero 0.5, area of cross section 2, divide by length 0.5, change in temperature 100 minus T naught. K2 0.3, area of cross section A, divide by length 0.4, change in temperature T naught. This A and this A will cancel out. 0.5, 0.5 cancel out. Point and point cancel out. So just cross multiply. So 8 times 100 minus 8 T naught equals to 3 times T naught. So 800 equals to 3 plus 8, 11 T naught. So T naught equals to 800 divided by 11. 11 to 7, 77, 30, 11 to 2.7 degrees Celsius. Hiba, you got the same or something else? Khalid, is it clear? Hamza, any doubt?
No, sir, no doubt.
Okay. You have reached up to this point or you are before?
No, sir, I was stuck before.
Okay, okay. Okay. Next is there will be another type of combination for which you have to calculate junction or temperature of junction. So for that part, let me define you about concept that is Kirchhoff's law of electricity, or it is also called Kirchhoff's current law, based on conservation of charge. To define this, let me give you an idea. Suppose you have any particular junction, this connected by 4 different roads at this point. If 3 individuals are coming from this way, 4 individuals coming from this way, and 2 has moved along this direction, so how many individuals will go along this way? Hiba, just tell me.
So can you repeat the question?
We have a junction, this, connected by 4 different roads. If there is no accumulation of individual at this particular junction, and for which we have 3 individuals coming from this way, 4 from this way, 2 has moved along this path, so how many individuals will go along this way?
The 3.
First, just count how many individuals are incoming to this particular junction. 3 from this way and 4 from this way. So 4 plus 3, total 7. So from this part, only 2 has moved along this way. So how many individuals moved along this way? It's 5. Okay.
Yes, sir.
So which principle we have used here? Total number of individual in coming to the junction must equals to total number of individual outgoing from this particular junction. Similarly, we can say about current according to conservation of charge. Sum of all current at junction will be 0, or total incoming current must equals to total outgoing current. Hamza, is it clear?
Yes, sir.
So according to conservation of charge, we can say if there is no accumulation charge at junction, then the algebraic sum of all current at junction will be 0, or sum of all inward current must equals to sum of all outward current. Hamza, any doubt?
No, sir.
Now, related to this part, you will be asked a question. Suppose you have 3 identical rods connected like this. Having temperature 90 degrees Celsius to this point, 30 degrees Celsius to this, and 0 degrees Celsius to this. So you'll be asked to find temperature of junction. First, write it down, then I'm defining how to solve this. Hiba, done?
Yes, sir.
Now for this part, just assume the temperature of this particular junction to be X. And by convention, take all current going outward, since we haven't any clue about which current must go inward and which current must go outward. So it will be better to take all current going outward. So let's say H1 along this direction, H2 along this direction, and H3 along this direction. So H1 equals to Ka by length times temperature difference X minus 90. H2 Ka by length temperature difference X minus 30. And H3 Ka by L temperature difference X minus 0. Since all current are going outward, so we just assume outward current to be positive. So according to the above formula, sum of all current at the junction must be equals to 0. As sum of all current at junction will be 0, it means H1 plus H2 plus H3 equals to 0. Ka by length X minus 90, Ka by length X minus 30, and Ka by L X minus 0 equals to 0. Take out Ka by L as common and simplify it to find the value of X. Hamza, is it clear?
Yes, sir.
Try to solve the value of X. Good, Khaled. Hamza, just tell me your answer. Take out Ka by L as common. So you're left with X minus 90, X minus 30, and X equals to 0. Move this coefficient to right side. So 0 divided by any constant will again become 0. Now X, X, and X, 3X, 90 plus 30, 120. So X equals to 40 degrees Celsius. Good, Hamza. Now, this is temperature of junction. Then next, you'll be asked to calculate heat current along each arm. So put this value of X in each term. So X is 40 minus 90. So you'll get minus 50 Ka by L. And second part, if you put X to be 40, so 40 minus 30, it will be 10 Ka by L. And third part, X is 40, so it will be 40 Ka by L. Now, the current, which is in negative term, it means the direction you have assumed must be opposite of it. So reverse this particular direction. So you'll get H1 inward and H2 and H2 outward. And if you add them all, you'll get total inward current must equals to total outward current. Hamza, is it clear?
Yes, sir.
Okay, just write it down. Salman, any doubt?
Yes, sir. My net is slow, sir.
Okay, no problem.
Done, sir.
Now, next concept is combination of rod, or how to calculate equivalent combination for series combination and parallel combination. So next is combination of rod. Let's say first is series combination. Suppose this is your first rod. This is second rod, which may have some different length as well, but area of cross section of both of them will be same. And for equivalent part, let's say this is first rod, thermal conductivity K1, length L1 from this point to this point, joined to temperature T1. This is another rod having thermal conductivity K2, length L2, and connected to temperature T2. Let's say temperature of this particular junction is T0. So on combining these two rods together, let's say this is equivalent rod of the combination of above to form single unit connected to one end at temperature T1 and the other end as temperature T2. Total length becomes L1 plus L2 and combined thermal length will be K equivalent. Hamza, any doubt related to these two diagram?
No, sir.
So let's say in first part, heat current will be through this first conductor will be H1, and through the second part, H2. And for this equivalent part, let's say H equivalent. So according to the formula, heat current through first rod, H equals to K A divided by length times temperature difference T1 minus T2. That is T1 minus T0. So move this T1 minus T0 to one side and rest of the term to other side. So you will write T1 minus T0 equals to H into length divided by K into A. Let's say this is first part, equation first. Similarly, heat current through second rod. So H equals to K A divided by length times temperature difference T0 minus T2. Since current flows from higher potential to lower potential, so in this part, heat will flow from higher temperature body to lower temperature body. So if you rearrange this particular expression to get T0 minus T2, it will be equals to H into length divided by K into A. Let's say this is equation 2. Hamza, any doubt related to this part?
No, sir.
Now add these two equations. On adding equation first and second, in left hand side we have T1 minus T0 plus T0 minus T2. For right hand side we have HL by K into A plus HL by K into A. So this T0 and this T0 will cancel out. So you're left with T1 minus T2 equals to H into length divided by K into A plus H into length divided by K2 into A. Let's say this is equation third. Hiba, any doubt?
No, sir.
Okay, just write it down to this. Hamza, done?
Yes, sir. Done.
Okay. Now for the equivalent part, we can write H equivalent equals to K equivalent times area of cross section, change in temperature T1 minus T2 by total length L1 plus L2. So on rearranging, T1 minus T2 equals to H equivalent into L1 plus L2 by K equivalent into area. Let's say this is equation 4. Is there any similarity between equation 3rd and 4th?
Yes, sir.
Hamza? Yes, what about? We have same temperature difference in both equation and left hand side. Now, since this particular combination is series, so for series combination, heat current will be same. So you'll say as H1 equals to H2 is equals to H equivalent in series. So from equation 3rd and 4th,
Sir, maybe has net problems.
okay. So on the basis of this part, let me give you a question. Suppose this is first rod and this is second rod. Thermal conductivity of this is 0.8 and thermal conductivity of this is 0.4. Length of rod from this point to this point is 0.4 meter. Point 0.1 meter. Then find K equivalent. Try to solve according to the above formula. So according to the above formula, L1 plus L2 divided by K equivalent, L1 by K1, L2 by K2. L1 we have 0.4 and L2 0.1. Divide by K equivalent, we have to calculate L1 0.4 divide by K1 0.8, L2 0.1 divide by 0.4. So on adding 0.4 and 0.1, it will be 0.5 by K equivalent. This part and this part will cancel out. So 4 in 2 times will be 8. So 1 by 2. This part and this part will cancel out. So 1 by 4. Now take LCM to be 4. So 2 times plus 1 times, that is 3 by 4, equals to 0.5 by K equivalent. So on cross multiplication, 0.5 into 4 equals to 3 times K equivalent, or simply K equivalent equals to 0.5 into 4, that will be 2 divided by 3, or simply 0.67 watt per meter per Kelvin. Is it clear?
Yes,
Or I
sir.
have done any mistake? No, I think my calculation is correct. Khalid, just check your calculation. Hamza, done?
Yes, sir. Done.
Okay. Similarly, you will be asked to calculate parallel combination. So next is parallel combination of rod. Suppose this is first rod, and this is second rod, having thermal conductivity K1 having thermal conductivity K2 and length of both rod is same. Let's say temperature of this end is T1 and temperature of this end is T2. Area of cross section of first rod is A1 and area of cross section of the second rod is A2. So on combining these two rods together, let's say total area from this point to this point will become A1 plus A2. Length remains same. Equivalent thermal conductivity K equivalent and temperature of both end, let's say T1 and T2. So for this part, we have to calculate similarly current for each segment. Now, let's say current across this H1. Heat current through first rod. So H1 equals to Ka by length, temperature difference T1 minus T2. Similarly, for second rod, heat current through second rod, H2 equals to Ka by length, temperature difference T1 minus T2. Now let's say for this equivalent part, and heat current for equivalent rod. So H equivalent equals to K equivalent times A1 plus A2 divide by length L times temperature difference T1 minus T2. Hiba, is it clear?
Yes, sir.
Just write it down to this part.
Done, sir.
Okay. Now, according to the concept of parallel combination, let me define you. Suppose you have a resistance this and a resistance this, whose both end connected together like this. So if current I is going across this part, so at junction, it may divide into two segments since we have two different paths. So I1 will move along this way and I2 will move along this way. So we can say at this particular junction, total inward current must equals to total outward current, or I equivalent equals to sum of all individual current. Is it clear? Similarly,
sir.
in this part, we can say H equivalent must equals to H1 plus H2. Now put the value of each term. So H equivalent we have K equivalent into A1 plus A2 divide by length times temperature difference T1 minus T2. H1 K A by length temperature difference T1 minus T2 plus K A by length temperature difference T1 minus T2. So we have same temperature difference on either side and length. So on combining, on cancelling out the equal term, K equivalent becomes K1A1 plus K2A2 divided by K1 plus K2. So this will be thermal equivalent for parallel combination. Just write it down.
Done, sir.
Salman, any doubt? Okay, so this is the entire part of heat conduction or heat current through any conductor. Next is radiation. So first, let me define you. What do you mean by radiation? To explain this, let me give you some basic concept. Suppose if you have any stone or any ball, and if you want to throw this particular object at some distance, so you must have to supply some energy to this particular object. So by taking this some amount of energy, it may move from this one point to reach at some other point. Hamza, is it clear?
Yes, sir.
But suppose there is a string on which you have strike from any hard object along this way. This jerk on this particular string may causes a disturbance like this. So this disturbance will propagate from one point to another, but without the displacement of matter particle. It means particle of this point of this string will tend to vibrate in their mean position and create a disturbance which propagates along the medium without the displacement of matter particle. So this phenomena of transfer of energy and momentum from one point to another is termed as wave. Hiba, is it clear? What do you mean by wave?
Yes, sir.
So wave is basically a phenomena of transfer of energy from one point to another without the displacement of matter particle. Of phenomena of transfer of energy and momentum from one point to another without displacement of matter particle. In general, we have three different types of wave. First is electromagnetic. Second is matter wave. And third is mechanical wave. Mechanical wave, a wave which require any medium for their propagation. So need medium for their propagation, just like sound. For matter wave, you must have learned about it in chapter 2 in chemistry, de Broglie hypothesis, which says every matter particle like electron, proton, neutron, alpha particle, they behave both as particle as well as wave. So you'll see wave associated with matter particle such as electron, proton, neutron are termed as matter wave. And next is electromagnetic wave, a wave which do not require any medium for their propagation and even travel through vacuum. So no need of medium for their propagation. Hamza, any doubt?
No, sir.
So from this part, you'll be asked, what do you mean by radiation? So you'll say, radiation is a type of electromagnetic wave. So it must have ability to travel through vacuum as well. And at what speed it may travel? So you will say at speed of light. So in general, this electromagnetic wave consists of 8 different waves in which cosmic rays, gamma rays, X-rays, UV rays, visible light, infrared rays, microwave, and radio wave. So in this part, we have to limit it only in this particular term. Visible region, the light to which our eye is sensitive to, that is VIBGYOR. And the next one, IR rays, or it is also called heat wave. Rest of all you have to learn it about in next class, that is in class 12. There was a special chapter or whole complete chapter about electromagnetic wave. Okay, so you learn it in more detail in next year. Okay, so just write down to this part.
Done, sir.
Okay, so from this part, we may define what do you mean by radiation. So you'll say radiation is a type of electromagnetic wave which does not require any medium for their propagation. Can travel through vacuum at speed of light. Now, related to this part, let me define you the first theory, which is called reversed hypothesis. It says every object which having temperature greater than 0 Kelvin will emit and absorb radiation at all time. So it says every object having temperature greater than 0 Kelvin will emit and absorb radiation at all time. Hamza, any doubt?
No, sir.
So related to this part, you'll be asked why we feel cold in front of ice and hot in front of fire. First question will be why we feel cold in front of ice, and similarly why we feel hot in front of fire. Any guess, Hamza?
Sir, because the temperature of the ice is lower than that of the temperature of our body.
So what will happen?
So um, I don't
Okay,
have
let me
more idea
explain.
about this.
Okay, no. According to Provost's hypothesis, which says every object having temperature greater than 0 Kelvin will absorb and emit radiation at all time. So first, try to calculate the temperature of these two interacting bodies. In general, human body having temperature 37 degrees Celsius. So if you convert it into Kelvin, it will be 310 Kelvin. And similarly for ice, 0 degrees Celsius. So in terms of Kelvin, it will be 273 Kelvin. Is it clear?
Yes, sir.
So we can say the more the temperature of body, it will radiate more amount of radiation. So from this part, we can say human body having temperature 310 Kelvin, so it will radiate more amount of radiation towards it, and ice being lesser amount of temperature, so it will radiate lesser amount of radiation towards this. So in which direction do you think there will be net flow of radiation? From human to ice or ice to human?
Human to ice.
Good. So net flow of radiation will be towards this. This net flow of radiation will tend to decrease the temperature of our body, but we are warm-blooded, so we can't change our body temperature. But due to this impact, energy or thermal radiation of our body may decreases, which will tend to feel cold. Is it clear?
Yes, sir.
Similarly, in this part, in front of fire, you can say the temperature of human body 310 Kelvin, and let's say temperature of fire to be 100 degrees Celsius. So in terms of Kelvin, 310, 373 Kelvin. So it will radiate lesser amount of radiation as compared to fire, and will radiate more amount of radiation since having larger temperature. So net flow of radiation will be from fire towards human being. So due to this net flow, which will tend to increase the temperature of our body, hence we feel hot in front of fire. Hiba, is it clear?
Yes, sir.
So for first part, we can write, since temperature of ice is low, so net flow of radiation will be from human to ice, which will tend to decrease the thermal energy. Hence, we feel cold. Similarly, in front of fire, since temperature of fire is more, so net flow of radiation will be from fire to human being. Which will tend to increase the thermal energy. Hence, we feel hot. Just write it down. Hamza, done?
Yes, sir, done.
Okay. Now, to define more theory related to this part, let me explain you some basic concept about it. First is absorptivity. which is also called absorptance or simply absorptive power. These all are same, represented by some A. Let me define you. Suppose you have any conductor placed over any burner or simply flame. So this heat or radiation falling on this particular object, let's say this is Q incident. So related to this radiation, we will have three different terms. Some heat may get reflected back from this particular surface like this. So this is called Q reflected. Some heat may get absorbed to this particular object. Let's say this is Q absorbed, and some heat may get transmitted along this. So it will be termed as Q transmitted. So depending upon this interaction, we may define three different terms. First is absorptivity, absorptance, or absorptive power. So it says the amount of radiation absorbed by object to the total radiation falling on it is called absorptive power or absorptivity. So it is just the ratio of total radiation absorbed by a body to the total radiation falling on it. So A equals to Q absorbed divided by Q incident. So this is nothing but ratio of same quantity. So its SI unit will be, or simply it will be unitless quantity. Now, depending upon amount of radiation reflected, we may define reflectivity or reflectance represented by R. So it is again the ratio of radiation reflected by a body to the total radiation falling on it. So R equals to Q reflected by Q incident. So it will be again in unitless quantity. Hamza, is it clear?
Yes, sir.
Now the third part which is called transmittance or transmittivity, denoted by T. So it will be the ratio of radiation transmitted by body to the total radiation falling on it. So it will be the ratio of radiation transmitted by a body to the total radiation falling on it. So T equals to Q transmitted divided by Q incident. So again, it will be unitless quantity. Now just write it down to this part. Hamza, done?
Yes, sir.
Any doubt related to this part?
No, sir.
Okay, let's stop here for today. In next class, we'll start with the rest part of radiation, in which I will define you about Kirchhoff's law of radiation, Stephen's law, and then Newton's law of cooling, the last part of this chapter. Okay? Okay then, take care. Allah Hafiz.
Thank you, sir. Allah Hafiz.